So welcome to the Tech Topic webinar of Industry 4.0 and Digital Twins in Engineering. We have some very special guests here today to speak to you. We've got Dr. Milind and Dr. Arti, both lecturers here at EIT, and they'll be providing a very informative session to you all today. So the session today will run for about 45 minutes, depending on how many questions we get throughout the session. We'll be providing you an introduction on both Milind and Arti shortly. We'll give you a brief overview of EIT, and then we'll dive into the session today with Milind and Arti. As I said before, please ask as many questions as you want, and we will try and get to your questions all today. And we will also do a question and answer at the very end as well. So we hope you enjoy it. I'm just going to hand over now to Milind and Arti, if you're able to give a little insight into both of your profiles, that would be fantastic.
Hello everyone, I hope you can see me as well. I have started my video feed. I'm Dr. Milind Siddhpura. I am actually a course coordinator and a lecturer at EIT. I'm based in Perth, at the Perth campus, but I actually coordinate courses all around the world, fully online and multiple campuses around the world as well. So I got, around 16 years of international experience in industry and academic. I have taught in various sectors, including, the vet sector in Australia. I did my PhD in mechanical engineering myself, and I have research interest in condition monitoring of machines and hydraulics and pneumatics, and I have received quite a few awards from Australian government as well. And I'm really pleased to have this opportunity to present to you this interesting topic. So, yep, welcome.
Hello everyone, I'm Arti here. I hope you can see me. And as you might have guessed from the names, it's a husband and wife duo. So Milind and I, we are both academics working in the field of mechanical engineering for more than 16 years. I'm a lecturer at the moment with EIT, teaching on campus and online, bachelor's and master's students. I have completed my PhD from the University of Western Australia, and yeah, the project was supported by CRC for infrastructure and engineering assessment, asset management. Basically, my main area of research interest is condition monitoring and automation. Main focus is improving unmanned tool wear prediction methods. It's really great to be here and to be able to present here. So welcome everyone, and thank you for joining us today.
Thank you so much, Arti and Milind. I will just give a brief overview of EIT and then I'll hand back over to you both.
Caroline.
Hi, Milind.
Sorry, are you taking over from here?
Oh, yep. I'll do this slide and then I'll hand back over to you.
Sure, thank you.
All right. So as most of you are probably aware, we're one of the only institutes in the world specialising in engineering. So we've been associated with the engineering industry for nearly 30 years. We actually grew from our sister company, IDC Technologies, back in 2008. And last year, we delivered our courses to over 2,000 students around the globe and have an alumni of students from over 140 countries around the world, which is quite incredible. We've got lots of programs ranging from professional development all the way through to a Doctor of Engineering. We've got an incredible network of over 300 industry-based expert lecturers around the world. And all of our programs are using a state-of-the-art technology using our remote and virtual laboratories, which makes us extremely unique in the online world. And finally, all of our programs are designed by industry experts to ensure that our students remain job ready at the end of their programs. Thank you, and I'll hand back over to Milind now.
Thank you, Caroline. Hello, everyone. Milind here again. So let me just first of all discuss the objectives of this particular webinar. So me in particular, I'll be discussing Industry 4.0. And under Industry 4.0, I'll be talking about basically definition. What is it? What is Industry 4.0? How Industry 4.0 would impact mechanical, mechatronics, and electrical engineers, and how it would impact civil engineers, and what you could actually do, how you could gear up your profession, which can actually lead you to Industry 4.0 qualified person. So you need to gear up to make it happen, so that you are actually compatible enough to work in Industry 4.0. And I'll be also talking about how EIT is gearing up for Industry 4.0 internally as a private engineering college. And then Arti will be talking about digital twins, and here are the objectives. She will be talking about what is digital twin, how does it work, uh, 3 levels of digital twin, its applications, different tools, and she will also be discussing some challenges in implementing digital twins. So let's begin. I'm quite excited. Are you excited, guys? So let me begin with my slide here. So I would like to first of all talk about what is Industry 4.0. What's this buzzword? Like everyone is talking about fourth industrial revolution. What is it? So let's actually explore that. So I would like to always tell a story, my presentation like a story. So I believe, human evolution was very slow over few millions of years. Humans were apes, and then they became cavemen, then they became farmers. But during over the millions of years when they were cavemen or farmers, they were relying on manual labor or animals to do farming and stuff like that until 17th century. So what happened in 18th century was very interesting. The first industrial revolution took place in the 18th century. So humans actually figured out that they can actually mechanize certain processes. They don't need to do the work themselves. They don't need to, put in bullocks in a bullock cart to do things on farms. So they mechanize. They realize that they can actually use steam power. They invented steam engine, and they also learn how to use water, hydraulic energy, to actually run the machines. So without human intervention, they actually develop these machines which can fully mechanize certain applications. So that was the first ever industrial revolution. The second one was all about mass production, because humans have invented electricity, and with the help of electricity they could actually create an assembly line to produce things. Now, first ever application of second industrial revolution was in slaughterhouse, but no one really remembers that because it's so cruel. So most of the people would remember Ford Motors company. So they actually invented first assembly line for producing cars. So that was happening in 19th century. So that was mass production in the second, and the third revolution took place in 20th century when we have invented computer. We invented PLC, which is programmable logical controller, and through which we achieved some automation. So in the third revolution, that was the robots working in the factories. They were autonomous, meaning that they were given certain commands and they were doing their job. In early 1990s, myself, I visited a Suzuki plant, and half a kilometer long workshop was full of robots. No man was present, or no worker was present, and it was fascinating. But there was still some limitation in that third revolution. The machine was running on its own. It wasn't actually communicating if it has some defects, some problems, some accidents. So that was overcome in the fourth revolution. So in today's age, what we call as Industry 4.0, machines, as you can see in the picture, can not only work on their own, they can actually communicate information between different machines. They can even talk with the servers, and they can actually uh, operate fully automatically and intelligently. They can make their own decisions. So that's what has changed in this fourth industrial revolution. And it's made up of cyber physical systems. So let me talk about what are cyber physical systems. So I'll give you a simple example. Let's say if you got a plant, let's say this is the plant which is housing so many machines in them, and there is a server. So this information in the middle is kind of a server which stores all the information. So whatever you're producing in your plant, the information is actually sent from the information center and it receives some control signals. So with these control signals, these machines are running. Now, in the fourth industrial revolution, these machines can actually talk with each other, as well as they can communicate their problems with the server. Now, if there is a problem encountered by the machines, uh, these problems would be communicated to the server. Server would then compute certain new parameters to actually to change the way the problem was occurring. So to avoid those problems, it would compute new control parameters, and control signals are sent again to the machines. And with these new control signals, machines can actually adjust and they can work on new control signals. So this is kind of a computation, communication, control, all integrated into one, which is called cyber physical system. So the top portion is all cyber system, and the physical system means your actual industry, your plant is a physical system. So I hope it makes sense. Moving forward, industry 4.0, what is it made up of? It is made up of 9 pillars. Now these 9 pillars, which will be mostly covered in the next part with Dr. Arti in digital twins, these 9 pillars are Internet of Things, big data, cloud computing, system integration, AR, which is augmented reality, simulation, autonomous robots, cybersecurity, and 3D printing, which is an additive manufacturing process. So what Industry 4.0 has done is it has integrated these 9 pillars to create an efficient industrial system that is not just automated, but it is intelligent enough to make their own decisions. So these are the 9 pillars. Moving forward now, okay, this is all about industry 4.0. Now, if you are already a mechanical, electrical, or mechatronics engineer, or if you are planning to study these disciplines, how can you adapt to this industry 4.0 revolution? First thing you need to remember that mechanical, electrical, mechatronics are like a basic branches of engineering, and they are the prime contributors to industry 4.0. Why? Because industry 4.0 actually connects physical and digital systems. So you need to remember that industry 4.0 is not about digital revolution. It's about manufacturing revolution. So without the underpinning knowledge of mechanical, electrical machines and systems, by just knowing some codes or software, you can't really do manufacturing revolution. So the mechanical, electrical, mechatronics engineers can actually do this manufacturing revolution, and they can create smart factories. So what is required under smart factories? How does it impact? So you need to understand, physical systems. As you know, you are being taught how the machines operate. That's what you need to know first. Then you need to upgrade your skills, formally or informally, to integrate those 9 pillars I discussed in last slide. You need to develop smart materials, sensors, miniature sensors, MEMS they call it, which are integrated in your machines as well. Automation of processes using robotics, and you need to also develop intelligent machines which are capable of communicating with each other in real time and make their decentralized decisions. So these are the ingredients of smart factories. And I would like to also let you know what are the major areas in these disciplines which are affected mainly. So mainly mechanical design is a kind of a branch of mechanical or even electrical or mechatronics. That's where computers would be creating algorithms, and these algorithms would run all the design drawings and revision of drawings and stuff like that. So no humans would be needed. Mechatronics and control, if you teach a machine how to make their own decision, you are no longer needed to actually give command to them. It can make their own decisions. Computational analysis like FEA and CFD, it could be also taught to computers and your systems. And finally, manufacturing, which is the key area which is going to be revolutionized, and integration of all 9 pillars and all of the above would be helpful in creating smart factory. So that's for mechanical and mechatronics engineers. The next one would be civil engineers. Now civil engineers would think, okay, it's not going to affect me much because construction is a different game. But no, it is not, because there will be always fewer boots on the ground as the time passes by, and more office-based, creative, and high-value roles will be created. Now as everyone knows, that we are moving towards driverless cars. So then why not machinery on a construction site driven by no one, driven by themselves, like machines themselves drive it, put the bricks on, put the roofs on, build the bridges. So in that case, what will change in civil engineering? Instead of infrastructure, it will become smart infrastructure. So all the buildings and bridges, they are all made smart. How can you do that? So more and more modular construction means prefabricated components would be used in building bridges and buildings. It is possible that additive manufacturing technologies like 3D printing could be building the whole houses or the bridges, the giant 3D printing machines. That is possible. The sensors would be fitted on the structures. So the bridges would be doing their self condition monitoring, means structural health monitoring of the bridges would be done by themselves, by the sensors fitted. The sensors talk to the cloud and cloud talks to the server, and server would manage everything. So structures can also be communicating with the contractors directly without involving any engineers. If they have some cracks in it, they can send a notification to the contractor that there are some cracks appearing on the pillars. Could you please come and fix that? Now, if you are a civil engineer, how you can adapt to Industry 4.0? Obviously, you'll need to upskill in electrical. Most of the electrical students I have taught, or civil engineering student I have taught some electrical unit, they would say, oh, why are we being taught electrical? We never use it. But it's no longer the case. You need to know electrical, you need to know programming, you need to know machine learning in order to adapt to Industry 4.0 for civil engineering. Now, you just need to imagine driverless cars going on a smart road or a smart bridge, and there is an accident. What would happen? There is no driver in the car is damaged, the bridge column is also damaged. In that case, the bridge can actually send that information about accident to the relevant authority, to the car manufacturer or car service people or the bridge maintenance people. They will send help. So that is possible when smart cars are be running on a smart bridge. So major areas to be affected in the civil would be again design, where computer algorithms are creating revising drawings, constructions where robots are actually building infrastructure without the need of engineers or construction workers. Maintenance, as I already mentioned, structures can self-identify the faults and they can arrange their maintenance needs without involving any humans. So these are the areas impacted in different disciplines. Now, the question is how you could really gear up for Industry 4.0 irrespective of what discipline you are in. My suggestion would be to pursue extra short courses, elective subjects. If you are still studying, take elective subjects in the area of programming. Take Python. Python is really trending at the moment. And once you complete your Python course, go for machine learning or big data analysis, IoT, and cloud computing. They are all interrelated, and there are short courses. And industrial automation, we have at EIT, industrial automation is also very, very popular because it involves all of these technologies, the 9 pillars. And another suggestion from me is to go for project-based learning. So if you are just learning Python, don't just learn and forget it. Try to implement the skills which you have learned into your real life project. If you're studying, try to apply that into the project which you have undertaken. If you're working in the industry, there would be a scope to take the skill on board. So practice and develop certain virtual reality or augmented reality based projects wherever possible. You need to also build truly multidisciplinary teams. So if you are in an industry or if you are running a company, try to make sure you have people from all the disciplines, mechanical, electrical, working together and having some solutions. Connect with industry experts, read certain technical papers, journals, and final suggestion from me is break the geographical barriers. Go online, take up the courses, which would be very, very valuable for your upskilling, and you would be able to gear up for Industry 4.0. So a question from me. I haven't been seeing any questions, sorry, because of presenting. What is your perception about Industry 4.0? How could you achieve it? In a couple of words, if you could write in the chat box, what is your perception about Industry 4.0? Yep, Rob, IoT for the supply chain. Definitely, supply chain is heavily impacted by IoT, and it's really, really good. Thank you, Rob. Anyone else? Yep, 5G will enable quick realization of Industry 4.0. Many outlandish expectations. That's true, Gary. It's like scope looks like endless, isn't it? But you have to take one step at a time in order to gear up for that. All right. Final word from me. EIT itself, as a private engineering college, we are also gearing up for Industry 4.0 for quite a few years through online learning. We have a range of short to long courses starting from certificate to diploma to bachelor's, master's, and recently we have launched doctorate in engineering, which takes care of all your needs for gearing up to Industry 4.0, which Caroline also mentioned in the beginning. So thank you from my side, and I'm handing over to Dr. Arti. Thank you.
Thank you very much, Milind. Now, before I start giving you a lot more information, plethora of information, I would say, about digital twin, I would like to know it from your side. What do you know about digital twin? What is your idea of a digital twin? Please let me know through the chat box, giving you a minute or two to present your ideas through the chat box, and then I will start my presentation based on that. Yep, so I can see a few replies in the chat box. Gary is suggesting it's a digital avatar. Rob suggesting aircraft design, build, and operation. It's possible through the digital twin. Yes, definitely. Product modeling, definitely that's part of digital modeling. GE digital twin, definitely we are going to talk a bit about that. Representation of a factory process in software or in its digital form. Yes, of course. Digital simulation of engineering machinery for effective maintenance and performance evaluation. Yes, definitely performance evaluation as well as maintenance and prognosis. A new dimension in which modeling designing can take place. Industry will impact HVAC field. Definitely. All right. Thank you very much, everyone. It's really good to see good response from you all. All right, so starting with digital twins, as I think Gary responded before during Milind's presentation, cyber physical production system. Now, this is a trending term nowadays, and as Milind has already covered, it's the core component of Industry 4.0. So basically, digital twin technology, it's an emerging concept that has become the center of attention for industry. And in more recent years, due to a lot of research going on, it is also a center of attention for academia. Now, advancements in Industry 4.0 concept, it has facilitated the growth of digital twin technology, particularly in the manufacturing industry. It's a virtual representation of a product which will allow you to understand how your product would perform before even you have built it. Now, that was a dream manufacturers were chasing since long. So even before you build something, you can completely analyze it, test it, and basically it's just the virtual counterpart of the product. The proliferation of sensors, faster computing powers, advanced data analysis techniques, and plethora of information technologies, they are all enabling further development of digital twins. Now, as we go through the evolution of this digital twin technology, we can see this diagram is basically showing us that. So this was before 80s, and that's the very first stage, that is digital enablement. Then came digitalization aided, and then there was digitalization assistance, and more recently it's cyber physical integration. So digital enablement basically refers to the process of converting paper document into digital forms, and that was before 1980s. So very basic form of digitalization. And next level was this digital aided, that is at the job level. So with extensive applications of computer-aided technologies, CAD, CAE, CAM in 1980s, the paradigm of this digitalization, it shifted towards assisting engineers to work with computers really effectively. So with the development of internet and then again advanced control technologies in 1990s, the next model was developed, and it was business digitalization, which provided new revenue and value producing opportunities. And after entering the 21st century, as we know, the new information technologies, IoT, cloud computing, big data, AI, to name a few, all those technologies are making it possible to progressively converge the physical and virtual worlds, basically cyber physical integration. And that is happening at industrial ecology digitalization, or at industrial level. Not just one particular business, not just one particular job, its entire industry is being revolutionized. All right, as we try to look into the origin of digital twins, we will soon end up with this name, Mr. Michael Graves. Now, he is the first one who coined this term, digital twin, in 2002. And here on this diagram, we can see the milestones, the major milestones of digital twin development. So basically, he coined the term, and then NASA adopted that. It was defined properly by NASA, and then so many other milestones were achieved as more technologies became available. So what is a digital twin? If we try to define a digital twin, there are quite a few scholars, quite a few researchers, academicians who have tried defining digital twins. So a lot of definitions are there. I have listed a few of them here. But instead of going into all those definitions one by one, let me try to explain it in the simple manner. It can, in my opinion, it can be best described as the effortless integration of data between a physical and virtual machine in either direction. So digital twin can communicate to the machine itself, physical machine, and physical machine can communicate back to the digital twin. And how does it work? So we have already briefly talked about various technologies enabling digital twins, but here is a list of some of them. So virtual reality, augmented reality, IoT, big data, cloud computing, machine learning, these are all enabling technologies which are assisting for the development of DT. It connects real and virtual worlds, and it collects the real-time sensor data using IoT connected sensors, which is stored in the cloud and then further analyzed and simulated in virtual copy of asset or products. And this simulation studies and data is then used to optimize overall product performance. As simple as that. Here is the three main elements listed for the digital twins. So first of all, we have sensors. So they capture operational behaviors of assets and processes like vibrations, temperatures, pressures, etc., alongside their functioning environments like air temperature, humidity, etc. So those are the sensors. And then we have communication networks over here. So they provide secure and reliable data transfer from physical device to the digital world. And then we also need a digital platform that serves as a modern data repository, which is pooling and storing the shop floor sensor data along with other high-level business data like manufacturing execution systems, MES, ERP, etc. And by combining these data sources, actionable insights can be derived from those data-driven decision-making using advanced AI and machine learning. And they do communicate among themselves. In order to simply show you the concept, here is an example of a car, digital model of this car. This is the digital model, and it has been created by using a 3D model of the car as well as getting real-time sensor data from the cloud. Now, the sensor data is coming from the product itself or the car itself, and it's going into the 3D model of the car. And then the data is used to analyze the vehicle performance on various parameters. So that is just an example. Now there are 3 levels of digital twins described in literature. The first one is considered as digital model. Now it is the version of pre-existing or planned physical object. The main thing over here, or main feature over here, is no automatic data exchange between physical model and digital model. Second level is digital shadow. So it's the representation of an object that has one-way flow of data between physical and digital object. Basically, change in the state of any physical object will lead to the change in digital object, but other way around, data transfer is not possible. If you make any changes to the digital object, it wouldn't affect the physical object basically. And then we have digital twin, that is the third level. So in this case, as we have already seen, the data flows effortlessly between physical object and digital object in both the ways. So from digital object to physical object and physical object to digital object. Next is digital twins applications, quite a few applications. I'm just trying to summarize a few. So through the integration with mobile internet, cloud computing, big data analytics, and other technologies, data is potentially applicable form in any field where it involves mapping, fusion, and co-evolution between physical and virtual spaces. So as we can see in this diagram over here, the DT applications, it can be found in smart cities. It can be used in construction, healthcare, agriculture, cargo, automobiles, aerospace, electricity generation. This is a cargo manufacturing, all those sorts of fields. DT is basically applicable almost everywhere. So here are major industrial applications or potential applications of digital twin technology. We can see quite a few applications, but if we try to summarize the main aspects, when it comes to predictive maintenance, digital twins are always applicable. Whether it's an aerospace engineering field, automotive, oil and gas, doesn't matter. Wherever predictive maintenance is required, we can definitely implement digital twins. Next bit is process planning and optimization. So that is another common factor where we can implement digital twins. And then product design and virtual prototyping is one next field where we can easily implement digital twins. So instead of reading through all those things, you can see prognosis and maintenance is one common thing coming up in all the applications. Design validation is another one. Maintenance, downtime prediction, those things are almost everywhere. Even resources allocation can also be done efficiently with the help of digital twins. If we focus mainly on the mechanical engineering related applications of digital twins, we can say that today's market is highly competitive, and the ambitions for shortening the time to market and for increasing the product development performance, those things are fueling actually the application of digital twins throughout all the stages of product realization. The biggest reason for this is that manufacturers are always looking for a way in which product can be tracked and monitored in an attempt to save time and money, obviously. So those are the key drivers and main motivational factors for any manufacturers. AI would improve the accuracy of testing as it can perform data analytics on real-time data to predict current and future performance of the product. Another thing, being able to see it before we build it. It has been a long time aspiration for manufacturing industry. Now, instead of building a prototype, if you can experiment on something which is pretty virtual, pretty harmless, it wouldn't destroy your prototype. How nice would it be? So the next identified application for digital twin is within manufacturing setting. The development stage of a machine or any plant is a potential application for digital twin. Use of digital twin and data analytics, it can potentially provide greater accuracy when predicting and maintaining machines and plants with any changes which is made virtually, and then we can apply those changes physically once we have studied them on the digital twin. So it gives design teams greater accuracy when carrying out simulation, as the algorithms can be applied in real time within the digital twin before any physical manufacturing starts taking place. And this technology can not only be applied in the development of product, but it is also as an ongoing real-time production and monitoring tool. It has the potential to give you real-time status on machine performance, as well as production line feedback. It gives manufacturer the ability to predict issues pretty sooner, even before they start taking place. And then they also increase the connectivity and feedback between the devices. So overall, improving reliability and performance. Industry 4.0 based main areas, as we have discussed, where digital twins can be implemented. That includes predictive maintenance. So gaining a holistic view of health and performance of equipment, companies can immediately detect anomalies, deviations in its operations, etc. Many times even before they happen. Process planning and optimization, so that can also be realized with the help of digital twins, and product design and virtual prototyping, as we have already discussed. Now, these were just the talks that digital twin can do this and that. What are the real world uses? Are there anyone who is using this new technology at the moment? So here are some of the examples where digital twin technology is being used in the real world. So a few industry partners, they created simulation model of operating pump, and then they can isolate the faults, perform diagnostics, and they can also recommend corrective actions. So that is one such application. Then another one is this Caser. They are transforming their business from product centering to service centering using digital twins to figure out the air consumption rate. GE, we briefly mentioned this. So digital wind farm solution, it collects and it analyzes the data from all the wind resources, and that is the biggest, one of the biggest names at the moment when it comes to the applications of digital twins. Apart from that, we have quite a few other scenarios, real world application scenarios. So Black & Decker, they are the power tool maker. They are implementing digital twins to encompass digitally modeling assembly lines and other factory systems. Rolls-Royce, even Formula One cars are being benefited by this digital twin technology. Chevron, GE, we have already discussed, and the digital twin of Singapore itself exists. And recently I came across a news that they have also created a digital twin of Shanghai. So those digital twins of the cities are also there. So those were some of the applications. Now, what are the tools for digital twin technologies? So here in this diagram, few tools are shown. It's a 5-dimension model. As we can see, there are 5 dimensions to that. 1, 2, 3, 4, and 5. So variable technologies are required to support different modules of digital twin, physical entity, virtual model, all those 5 dimensions. So for physical entity, full understanding of physical world is a prerequisite for DT. It involves multidisciplinary knowledge. That includes the knowledge of dynamics, structural mechanics, acoustics, thermals, electromagnetism, material science, control theory, to name a few. So engineers would always be needed in order to perform this part of digital twin modeling. So digital twin is to create that virtual model for physical entities in the digital way to simulate their behavior. Physical world is the foundation for DT. It has always to deal with the physical world. It may consist of a device, product, physical system, activities, process, or it could be entire organization itself. So they implement activities according to physical laws, and it deals with certain uncertain environments. Now, these physical entities, it can be divided into 3 levels according to function and structure. So which are unit level, system level, and system of system SOS level. So that is about the physical entity part. Then comes digital twin data part, the second bit. So twin data is a key driver for digital twin technology. It requires a lot of data, and it deals with multi-temporal scale, multi-dimension, multi-source, and heterogeneous data. Some data is obtained from physical entities, including static attribute data and dynamic condition data. Some data is generated by virtual models, and it will reflect the simulation results, etc. So data basically is obtained from services, and it describes the service invocation and execution. The next aspect is services in digital twin. So moving on to the services. Against the background of product service integration in all aspects of modern society, more and more enterprises are beginning to realize the importance of service. It is an essential component of digital twins in light of the paradigm of everything as a service. And DT provides user with application services concerning simulation, verification, monitoring, optimization, diagnosis, prognosis, health management, etc. Secondly, number of third-party services are also needed in the process of building a functioning DT, like data services, knowledge services, algorithm services, etc. And lastly, the operation of DT, it requires the continuous support from various platform services, which can accommodate customized software development, model building, service delivery, etc. So that was the service part. Coming to the connections. So digital representations, they are connected dynamically with their real counterparts to enable advanced simulation, operation, and analysis. Digital twin cannot be isolated from its physical counterpart. So we have to have some sort of connections between physical entities, virtual models, even between services and data, enable information and data exchange. Basically, there are 6 connections for DT. They all actually interact among themselves. Services do interact with data and data with services. Services do interact with model and model with services. Physical and model, model and data. So this 6 different kinds of connections are needed there in digital twins. Now here, this diagram shows the framework of tools for digital twin. Each and every dimension of digital twin and what sort of tools are needed there has been described in this one. For example, the tools for physical world, what do we need? Sensing the physical world, tools for adjusting the physical world, etc. So all different tools. And here we can see the tools for cognizing and controlling the physical world, tools for connection, various tools for digital twin modeling, various tools for digital twin data management, and various tools for service applications. So all 5 dimensions of digital twin model and require tool for each and every dimension. All right, so that is about enabling technologies and tools. Moving on to the last bit, and that is the challenges. So what are the challenges? This is comparatively a new technology, and obviously it's not free from the challenges. We are still trialing it out. We are still experimenting with that. So quite a few challenges associated with them. Data analytic challenges are all here. I wouldn't go into a lot more details of this or even IoT and IIoT related challenges, but we will briefly discuss digital twin challenges. So first challenge is IT infrastructure. Sorry, the first one I would consider is the data, mainly the privacy and security of data, instead of discussing it over here. So we are basically dealing with a lot of data, and bigger data comes with bigger challenges. So it could be sensitive data, it could be value to a criminal, and it could increase the threat due to that. And the threat is significantly increased for businesses when they could be dealing with sensitive customer data. So data safety, security, and privacy is one such challenge. Apart from that, we have IT infrastructure challenge. So basically, the infrastructure currently in place is behind due to that really rapid growth which IoT technologies have observed nowadays. So that is another challenge. Then we have the challenge of dealing with useful data. Now, we have so many sensors giving us the real-time data continuously, but we need that data to be really high quality data. It should be noise-free with constant uninterrupted data stream. So poor and inconsistent data can increase the risk of digital twin underperforming or misinterpreting that. So that is another challenge there. Privacy and security. So within an industry setting, it is clear that privacy and security associated with digital twins, they are a huge challenge because the vast amount of data they are using and the risk this poses to sensitive system data. Next, we have trust issues. So the challenges associated with trust are both from an organization point of view as well as the user point of view as well. This digital technology needs to be discussed further and explained at a foundation level to ensure that end users and organizations, they all are aware, they are all on the same page, they know the benefits of digital twin and what sort of challenges will they bring with them. Next is expectations. So despite this digital twin adoption being accelerated by industry leaders like Siemens and GE, caution is needed to highlight the challenges that exist for the expectations of digital twins, and obviously there is certainly a need for more understanding. Standardized modeling, now as I've already mentioned, it's a more recent technology, it's pretty new technology. So the next challenge within all forms of this digital twin development relates to the modeling of such systems because there is no standardized approach to modeling. From initial design to a simulation of digital twin, there needs to be a standard approach, whether it be physics-based or design-based, but some sort of standardization is definitely needed there. And finally, we have a challenge associated with domain modeling. So it's as a result of need for standardized use. It's related to ensuring information relating to the domain use is transferred to each of the development and functioning stages of the modeling of digital twin. Now, this ensures compatibility with domains such as IoT, data analytics, and allowing for successful uses of digital twins in future. So those are some of the challenges, and maybe if you have an idea, rough idea how to overcome that, probably can lead you in direction of further research. And here are the references. Now, before I formally open up for questions and answers, just quickly going back and having a look at what we've discussed today. So we had a look at Industry 4.0, application mechanical, mechatronics, civil engineers, and gearing up for that. And then we also discussed about digital twin, how it works, tools and technologies, and challenges associated with digital twins.
Thank you so much, Arti and Milind. That was brilliant. I've learnt so much myself, and I'm obviously not in engineering, but that was great. There are a few questions I'm going to ask both of you in a moment, but just for everyone online right now, we would love to create a certificate for obviously your attendance. So please email the email address up on this screen if you would like us to organise a personalised certificate for you to utilise in whatever you would like to use it for. So please feel free to email us on that email address and just note your full name and obviously the email address you want us to send it back to. And then I'll pass back to questions. I've just got a few questions here, Arti and Milind. Ivana asked, does the fact that there is DT in smart cities mean that all the processes like water use, electricity use can be managed better?
Yes, definitely. Smart cities in their digital twin form, they can enable the teams to take so many decisions, and they are having all those minor details integrated into them. One of the new capitals of one of the states in India, they developed it completely based on digital twins, and I've heard they even planted the trees based on their modeling and simulation on its digital twins. So yeah, basically, definitely it has all those things into it.
Great. And one from Rob, will EIT be running a BIM course covering data capture, modelling, simulation? I'm not sure if you've both heard any talk about potentially running a course around
Hi, Rob.
this.
Thank you. Thank you for your question. Not currently we are running any course on building information model. Right now we have in civil and structural area, we got civil and structural engineering in bachelor's and master's. But possibly in future, we may plan for a BIM course, Rob, but not at the moment. Thank you.
Thanks, Milind. Gary also had a question, but I'm not sure if you guys are able to see it, just because there was quite a bit of information. Just at 4:27 p.m. I'm not sure if that's popped up on your screen. It's just above Rob Sawley's comment about augmented reality technology. He's just made a comment saying no mention of quantum computing related blockchain technology to be incorporated in digital twins. I'm not sure if you've got any comments on that.
Thank you for that comment, Gary. Definitely, it could have included. It's such a vast field and it's such a short time. So obviously, it won't be possible us to touch base on each and every aspect. But this is what we tried from our side. But thank you very much for your comment.
Thanks, Arti. Has anyone got any other
also
questions?
the blockchain and quantum computing would be a subset of the technologies which Arti has discussed already. So it would be still be present somewhere in it. Thank you.
Thanks, Milind. Has anyone got any other questions before we wrap up the session? I've just got up on the screen. We've got obviously a email address at the bottom of that screen as well. So please feel free to email that if you've got any direct questions. But otherwise, we'll be sending out this recording hopefully tomorrow to everyone that's joined. Yes, Hermanus, we'll be sending out the recording, not a problem at all. But yeah, as I've said before, if anyone's got any other questions that come to mind, please feel free to send it through to us, and I'm sure Milind and Arti would be happy to answer them over the next week if you think of anything else. But otherwise, we hope you enjoyed today's session, and a very, very big thank you to Milind and Arti for sharing your knowledge today. And we'll be running our next tech topic on Industry 5.0 at the end of next month. So we'll be sending out some information over the next 2 weeks. But thank you again, Milind and Arti, and I'm not sure if you want to say any other final comments before we wrap up.
I would like to say thank you everyone for attending this, and thanks Caroline for organizing this event. Thank you.
Thank you very much, everyone, for attending this one. And of course, thanks to you, Caroline, for organizing.
Thank you both, and have a wonderful evening. And if anyone's starting their day, have a wonderful day. And we hope to see you on one of our next webinars. All right, thanks all. Bye.